The key to resolving the paradox of entropy at the Big Bang lies in the special nature of the universe's initial conditions. If we consider that the universe began in a state of extremely low entropy, represented by an extraordinarily small, coarse-grained region in phase space, the past behavior of systems becomes understandable. The special nature of the initial state at the Big Bang provides a theoretical basis for the second law of thermodynamics. Since the universe began with very low entropy, all physical systems have since evolved to states of higher entropy. This creates the arrow of time that we experience as entropy increases as we move into the future. This gradual increase in entropy is consistent with the second law and explains why systems become more disordered over time. The initial conditions of the universe effectively drive the entire evolution of the cosmos toward states of higher entropy. The special initial state of the Big Bang is central to understanding the second law. Without this low entropy starting point, the logic behind the second law would break down, and we would not observe the increasing entropy we see in the world around us. We also need to address the relationship between the second law and our experience of time. Some argue that the flow of time as we perceive it is related to an increase in entropy. In other words, our consciousness may be wired to always experience time in the direction of increasing entropy. If the entropy of the universe were decreasing, we would perceive time as flowing in the opposite direction. According to this view, the psychological arrow of time is tied to the thermodynamic arrow of time, and regardless of the underlying physical processes, we would always see the future as the direction of increasing entropy. This argument provides a possible explanation for why we observe that the second law always holds. Even if entropy were decreasing in a different time direction, our perception would still be calibrated to experience time in the direction of increasing entropy. Therefore, the second law would always appear to hold from our subjective perspective, even if the physical flow of entropy were reversed. We have emphasized that the special initial conditions of the universe give rise to the second law of thermodynamics and the asymmetry between the past and the future. The fact that the universe begins in a state of extremely low entropy explains why systems tend to evolve toward higher entropy as time progresses. One of the paradoxical conclusions we reach when reasoning backward in time is that the Big Bang was constrained by low entropy boundary conditions. This special initial condition makes past teleology part of our everyday experience, while future teleology seems impossible. The arrow of time, dictated by entropy, moves forward from the Big Bang and shapes the evolution of the universe. This understanding provides a robust explanation for the second law and the irreversibility of time that we observe in the physical world. The idea that the passage of time, the existence of life, or the operation of the second law can be fully explained by subjective experiences or life-related processes is open to debate. If we begin by rejecting the argument that our perception of time is inherently dependent on increasing entropy, which is why the second law holds, because we experience time as progressing with increasing entropy. This argument, which assumes that our psychological experience of the passage of time is shaped by increasing entropy, must be rejected both speculatively and to explain the universal application of the second law. The real problem here is that entropy is useful as a concept only because our universe is far from thermal equilibrium. If the universe were at or near thermal equilibrium, where entropy is at its highest, there would be no significant differences between the coarse-grained regions of phase space, making the concept of entropy meaningless in practical terms. However, in our current universe, we live in a region of phase space that is much smaller than the region of maximum entropy, which allows for significant entropy differences between states. The behavior of uniform entropy, whether it is increasing or decreasing, depends on the initial and boundary conditions of the universe. In particular, the reason we observe uniformly increasing entropy is that the universe began in a state of extraordinarily low entropy, represented by a very small, coarse-grained region in phase space. It is this small initial region, not the observation of increasing entropy, that requires explanation. The second law holds only because the evolutionary curve of the universe begins from this restricted initial condition, and this starting point has far-reaching implications for the thermodynamic behavior of the universe. This argument also rejects anthropic reasoning, the idea that the second law is a necessary precondition for the existence of life and therefore the reason we observe it. Although life as we know it depends on increasing entropy, this reasoning does nothing to explain why the second law holds universally, even in regions of the universe, or at times completely unrelated to the development of life. The second law holds at very large distances, such as galaxies billions of light years away, and at times long before life emerged on Earth. The existence of life on Earth cannot serve as an explanation for the global application of the second law. Consider the special initial conditions of the universe, specifically the low entropy starting point that accounts for the increase in entropy over time. The Big Bang represents an extraordinarily low entropy state, and this starting point places a constraint on the evolution curve of the universe. Since the universe originated in a very small, coarse-grained region, entropy has been increasing ever since. Without this special initial condition, we have no reason to expect the second law to hold. The evolution of the universe could theoretically proceed without entropy constraints, leading to a universe in which the random assembly of life or miraculous events, such as self-assembling eggs, would be more likely than the natural processes we observe. In such a universe, the second law does not govern thermodynamic behavior. The universe's initial low-entropy state is an extremely rare configuration in phase space, and this rareness is what drives the increase in entropy. If the universe had not started in such a constrained state, we would not observe the uniform behavior of the second law. The existence of life cannot explain the origin or universality of the second law, since the latter is a product of the initial conditions of the universe. The second law has the potential to be reversed in the distant future. While the second law is well supported by observations of the early universe, we have little evidence for the distant future of the universe. Given the large timescales involved, the entropy of the universe may reverse after orders of magnitude longer than the time since the Big Bang. The idea is that if the evolutionary curve of the universe is constrained to end in another small, coarse-grained region similar to the initial state, we will eventually see the entropy begin to decrease. This would result in teleological behavior in the future, where systems evolve into more ordered states, as absurd as this may seem from our current perspective. This scenario is rejected as highly implausible and has little to do with the universe we currently observe. However, this possibility is not inherently absurd within the framework of Newtonian dynamics or the fundamental laws of physics. Just as the universe began in a low-entropy state, there is no intrinsic reason why it should not end in a similarly constrained state. However, such evolutions would be extremely rare, even rarer than the already rare low-entropy initial state of the universe. The low-entropy initial state of the universe is the critical factor behind the second law of thermodynamics. The observed increase in entropy is not a result of life, consciousness, or anthropic reasoning, but a result of the universe's special initial conditions. While speculative ideas such as a future reversal of the second law cannot be completely ruled out, they are unlikely and are not supported by current observations. Let's examine the open questions of cosmology related to the entropy concept. The inflationary model of the early universe proposes that, in the first fraction of a second after the Big Bang, the universe underwent a period of extremely rapid exponential expansion. This inflationary phase, first introduced by Alan Guth in the 1980s, addresses several cosmological puzzles, such as the flatness problem and the horizon problem. But more subtly, it also plays a key role in shaping the universe's time asymmetry. To understand time asymmetry, let's first recall that the fundamental laws of physics, such as Newton's laws or Maxwell's equations, are time reversible. They don't distinguish between moving forward in time or backward. Yet, in our everyday experience, time flows in one direction. This is often referred to as the arrow of time, and it is closely tied to the second law of thermodynamics, which states that entropy, the measure of disorder, tends to increase over time. In essence, the second law demands that the universe evolves from states of lower entropy to states of higher entropy. One of the central questions in cosmology is why the universe began in such a low entropy state. After all, if the universe began in a high entropy state, we would expect little order or structure to form. Cosmic inflation offers a possible answer. Before inflation, the universe was likely in a chaotic, high-entropy state. During inflation, this chaotic state stretched out, essentially diluting the universe and smoothing it into a low-entropy condition on a large scale. This inflationary process sets the stage for the subsequent growth of complexity, as quantum fluctuations during inflation were magnified and seeded the structures we see in the universe today, such as galaxies and clusters. This stretching also amplifies time asymmetry. Inflation creates a clear distinction between a before, a disordered high-entropy state, and an after, a highly ordered, low-entropy universe ready for structure formation. It is this transition that gives rise to an arrow of time that aligns with the second law. From a cosmological perspective, time asymmetry seems to arise naturally out of the inflationary model. Now, consider the second law in the context of an expanding universe. As the universe expands, it creates room for entropy to increase. Initially, the universe was extremely hot, dense, and relatively homogeneous, states of low entropy compared to the highly structured universe we observe today. Inflation allowed the universe to expand and cool rapidly, creating the conditions for entropy to grow as stars formed, galaxies coalesced, and complex structures emerged. Because the early universe began in this low entropy state, as dictated by inflation, the second law drives the arrow of time forward as entropy increases. The expansion of the universe gives physical space for entropy to evolve, creating the conditions necessary for time's one-way flow. Interestingly, during inflation, quantum fluctuations become magnified and play a crucial role in the development of large-scale structures. These fluctuations create tiny variations in the distribution of matter, which eventually lead to the formation of galaxies and clusters. However, on a quantum scale, these fluctuations themselves do not possess a preferred time direction. They are, in a sense, time-symmetric. It is the inflationary process that takes these time-symmetric quantum fluctuations and imprints upon them a directionality, establishing a macroscopic arrow of time by setting the initial conditions for the universe's entropy evolution. In this way, inflation transforms an underlying symmetry at the quantum level into a macroscopic time asymmetry. The early universe's extremely low entropy state could be seen as a necessary condition for the second law to hold sway throughout cosmic history. Without inflation, it would be difficult to explain why the universe started in such a state. Inflation provides a mechanism by which a high-entropy, chaotic primordial state can be stretched into the smooth, low-entropy starting point that allows for time asymmetry and the forward evolution of entropy. The second law of thermodynamics asserts that entropy tends to increase, and that's precisely what has been happening since the Big Bang. The early universe was smooth and homogeneous, with low entropy, but over time, gravity caused matter to clump together, forming stars, galaxies, and planets, thereby increasing entropy. The growth of structure in the universe, clustering of matter into galaxies, formation of stars, and eventual formation of black holes, is a manifestation of increasing entropy. The formation of complex systems, though appearing ordered from our perspective, actually increases the overall entropy, because these systems release vast amounts of energy in the form of heat and radiation into the cosmos. So, what does this imply for the future evolution of the universe? There are several scenarios, but the direction in which entropy evolves remains key. One widely discussed possibility is the so-called heat death or Big Chill scenario. In this model, the universe continues expanding indefinitely. Over time, stars exhaust their nuclear fuel and eventually die, galaxies drift apart, and black holes evaporate via Hawking radiation. Without new sources of energy or matter clumping together, the universe reaches a state of maximum entropy, where everything is in thermal equilibrium. In this ultimate future, the cosmos would be cold, dark, and featureless, a diffuse spread of low-energy radiation and particles. This is the end state of entropy, a universe where no further thermodynamic work can be done, and time, as we understand it, essentially loses meaning because there's no change, no events, and no distinction between past and future. Another possibility, though currently less favored given observations of the universe's accelerating expansion, is the Big Crunch. In this scenario, if gravity was strong enough to overcome the expansion of the universe, everything would collapse back into a singular point, reversing the process of cosmic inflation. In such a scenario, entropy would increase dramatically as the universe collapses into a hot, dense state, reminiscent of the high-entropy chaos before inflation. This would be a dramatic, fiery end, but still consistent with the second law, as entropy would have increased throughout the collapse. In another alternative called the Big Rip, if dark energy behaves in a certain way, the universe's expansion could accelerate to the point where it rips apart galaxies, stars, and eventually even atoms. This scenario also leads to a high-entropy future, but through a violent disassembly of all structures. While inflation provides a plausible explanation for how the universe started in a low-entropy state, there's a deeper mystery here. Why was the pre-inflationary universe in a state that allowed for inflation to begin? Some physicists speculate about a multiverse or eternal inflation model, where our universe is just one of many. In this view, inflation occurs in different regions of space at different times, with some regions, like ours, transitioning into low-entropy states, giving rise to distinct universes. This multiverse framework might help explain why our universe happened to emerge in a low-entropy state, but it also opens up new questions about the nature of time and causality on a larger scale. One teleological concept that often arises in cosmological discussions is tied to the anthropic principle. The anthropic principle suggests that certain features of the universe are as they are because they allow for the existence of observers like us. In other words, the universe's properties might seem fine-tuned for life because, out of a multiverse of possibilities, we happen to exist in one where life can arise. In this view, the universe's future evolution isn't necessarily driven by a goal, but it might appear as if it is directed toward supporting complexity, life, and intelligence. This could be seen as a kind of teleological interpretation, where the conditions we observe seem purposeful because they support conscious beings capable of observing the universe. The anthropic principle itself doesn't violate the second law, because the low-entropy conditions of the early universe and the evolution of structure, such as galaxies, stars, and life, lead to increasing entropy over time. The eventual fate of the universe, whether it be heat death or something else, still involves a continual growth of entropy. Any purpose we perceive in the universe's evolution is merely a consequence of our existence in a very specific pocket of low entropy. Some cyclic cosmological models propose that the universe goes through infinite cycles of birth, death, and rebirth. The most famous historical example of this is the oscillating universe model, where the universe expands from a Big Bang, eventually collapses back in a big crunch, and then rebounds into a new Big Bang. This process could, in principle, continue forever, repeating cycles of cosmic evolution. In modern times, a more developed version of this idea is found in the ekpyrotic model, based on string theory, where our universe is periodically reborn through the collision of higher dimensional branes in a higher dimensional space. In this model, each cycle includes a Big Bang-like expansion and subsequent evolution, with entropy being reset at the start of each new cycle. One might be tempted to interpret cyclic models as teleological since they suggest a repeating pattern, an eternal recurrence of similar states. However, from a purely physical perspective, these models don't imply any particular goal or purpose to the universe. Instead, they describe a continual process of cosmic recreation. A challenge for any cyclic model is how to reconcile it with the second law of thermodynamics. After all, in each cycle, entropy increases, so how could the universe reset itself for another cycle without violating the second law? One solution proposed in some models is that during the collapse phase, before the next Big Bang, the universe could be scrambled in such a way that entropy is somehow reset. In the ekpyrotic model, for example, the energy released in the collision of branes could effectively reset the entropy clock, allowing the second law to restart in the next cycle. Now we venture into more speculative terrain with the idea of the omega point, first proposed by physicist and mathematician Frank Tipler. The omega point is a vision of the distant future of the universe in which, rather than decaying into entropy and heat death, intelligent life plays an active role in shaping the future of the cosmos. According to this hypothesis, advanced civilizations could harness energy and manipulate matter to stave off entropy, eventually reaching a state of near omniscience and omnipotence as the universe approaches an asymptotic final singularity. In this scenario, intelligent life continues to evolve and expand its reach throughout the cosmos, potentially even reversing the effects of entropy locally through advanced technologies. The universe might then culminate in a sort of conscious, unified state, the omega point, where everything is brought together into a final, ultimate form of intelligence. The omega point hypothesis runs into serious challenges with the second law of thermodynamics, since it posits that intelligence might find a way to control or even reverse entropy. Tipler's idea suggests that as the universe contracts or collapses, advanced civilizations could somehow access increasing amounts of energy to perform infinite amounts of computation, even in a universe that is approaching a state of collapse. Most physicists remain skeptical of this model because it requires extraordinary assumptions about the abilities of future intelligences and exotic mechanisms for circumventing the second law. While intriguing, it remains highly speculative and not widely accepted within mainstream cosmology. Finally, there's a softer form of teleology suggested by complexity theory. As entropy increases, local systems can undergo phases of self-organization and complexity. Life is a prime example of this. Although entropy increases globally, pockets of low entropy give rise to complex systems like stars, planets, and eventually, life itself. Some cosmologists speculate that life and intelligence may represent an emergent phenomenon in the universe, driven by the universe's expansion and increasing entropy. This isn't teleological in the traditional sense. There's no goal the universe is aiming for. But from the perspective of life and intelligence, it may feel as though the universe has a purpose, because complexity grows and intelligence evolves, even while entropy increases. The second law is fully respected in this model. The creation of local complexity, such as life, requires energy dissipation, and in the process, the universe's overall entropy continues to increase. Thanks for listening, and take care.